Next thing we're going to look at, inequalities. Now, first idea with inequalities, we've seen it before, is using graphs to solve inequalities. So we'll start off with one like this. X squared on x plus 2 is less than or equal to 1. Now, I'm not suggesting necessarily this is the way to go and solve it. But if we were to draw the graph y equals x squared on x plus 2, so it's my red parabola divided by my blue line, I'd have an asymptote at -2, break it up into its areas so I know where it's positive and negative. I know it's going to have an oblique asymptote, because when I do a polynomial division I get x minus 2 minus 4 and x plus 2. So there's my oblique one, and there's my curve. We're saying, when is that curve below y equals 1? So if I draw in y equals 1, we can see there's actually two sections, this bit over here on the left, and between these 2 points of intersection. So I'm still going to have to find the points of intersection, unless I happen to have an incredibly accurate graph, which in this case I do. It happens to fall exactly on whole numbers, so that worked out nice. So x equals 2, x equals minus 1. So putting it all together now, we can see it's okay when x is less than -2, or x is in between minus 1 and 2, but including the minus 1 and 2. So I don't reckon it's a wonderfully efficient way of solving the inequalities, but if you happen to have drawn the graph already, it might save you some time. I'm probably thinking more, when I talk about inequalities in graphs, the idea that we looked at when we introduced integration, with the outer rectangles, inner rectangles, that sort of idea. So, quite an old question now, 1990. They've given us the graph y equals the square root of x, and drawn some of those outer rectangles in. The first thing they want us to show is, the graph is continually increasing. So we differentiate, and 1 on 2 root x, and of course that is always positive. So for x is greater than 0, the derivative is greater than 0. I don't know why I bothered doing the next bit, but it does start at the point 0, 0. So, and when x is greater than 0, y is greater than 0, thus confirming that even from its initial point, it's going up. Perhaps I did that because my derivative wasn't defined at 0, but my function was. So I wanted to show that, it does actually increase from the starting point. Might have been a bit of overkill, that bit. They probably were only just looking for derivatives greater than 0. So is increasing for x is greater than or equal to 0. Okay, here's the expression we have to show. And I guess they gave us the clue by drawing the rectangles in for us. So we're going to talk about the outer rectangles, because the outer rectangles will be greater than the actual integral itself. So there's that picture again. Now we know it's increasing, so therefore, due to the concavity of the curve, every one of these rectangles will be above the curve. So the first one would have an area of square root of 1, next one square root of 2, and so on and so on and so on, up to the square root of n. So we've got the first part. Now we just have to evaluate the integral itself. And sure enough, we get our 2/3 n root n. Okay. Now we're going to use induction to show that that same series is less than or equal to, well, they've given us 4n plus 3 on 6 times root n. Alright, well, first case, left hand side's 1. Right hand side we get 7 on 6. Now they have said less than or equal to. We've shown it's less than, so therefore it's less than or equal to. I'm going to assume my results. We're going to want to prove it for k plus 1. So that's where we're trying to head to. 4k plus 7 on 6, square root of k plus 1. So it's a series type. I'll rewrite it as sum to k plus root k plus 1. Our assumption was 4k plus 3 on 6 root k. Remember, we're trying to get, 4k plus 7 on 6 times the square root of k plus 1. Okay, how am I going to manipulate this? If I turn it all into one fraction, well, at least I've got the on 6. There's a start. I've got 6 lots of root k plus 1, but we want 4k plus 7 lots. Okay. So this first third, I want to end up showing, what is it going to be? 4k plus 1 lots of root k plus 1. If I actually expand out that 4k plus 3 squared times k, and if I factorise it, but with a little bit of a difference. So I've taken out a factor of k plus 1. And the reason I did that is because I know I want to show multiple of root k plus 1. But of course it doesn't go in exactly. If you do the polynomial division, you get left a remainder of minus 1. But we're dealing with inequalities, remember. I factorised the 16k squared plus 8k plus 1. But therefore, if that expression minus 1 has got to be less than the square root of k plus 1, 4k plus 1 squared. That gets me the 4k plus 1 lots of root k plus 1 I'm looking for. And so there's our 4k plus 7 lots of root k plus 1 that we're trying to prove. Okay. Hence the result's true for k plus 1. Oh, that's the old way we used to do it. Very verbose. Says it's true for n equals 1 and so on and so on and so on. Aren't you glad we don't have to do that anymore? But now what we've done is we've trapped our series square root of 1 up to the square root of n in between two expressions. And we're going to use that to evaluate up to the square root of 10,000 to the nearest 100. So we've trapped it in between 2/3 n root n, and on the other side 4n plus 3 on 6 root n. So if we substitute in 10,000, you'll find a wonderful thing happens when you evaluate the left hand side and the right hand side. But remember, we're only evaluating it to the nearest 100. To the nearest 100, both ends turn out to be 666,700. Well, so if it's in between them, well, we know what it is to the nearest 100. So it's going to be 666,700 to the nearest 100. Quick little one. Going to prove x is greater than sine x. And there's lots of different ways of doing this inequality. I'm going to do it graphically. There's y equals x. And sine x. What are we basically saying? We want to prove that that line y equals x is always above the sine x curve when we're talking about positive numbers. Sure, I can say, oh, look at the picture, it's always above, but that's not a real good proof. But if I look at the derivative, I know the slope of that line is 1. And I know the slope of sine x will always be cosine x, depending on the x value. But I know cosine x, the biggest that's ever going to be, is 1. And that's going to happen for the first time over here at pi on 2. And when we get to pi on 2, y on x is already bigger than 1. So there'd be no value there where that gradient is shallower than the red curve. So if it's always steeper, then it must be rising quicker. Now they started at the same point, 0, 0. So if the line's rising quicker than the red curve, it's always got to be above it. That's the basic idea I'm using here. So I'm saying, well, between 0 and pi on 2, I know cos x is always less than 1. Well, it's equal to 1 over at pi on 2. So y equals x will increase faster than y equals sine x. So therefore x is always going to be greater than sine x. Now, once it's bigger than pi on 2, it's kind of trivial, because the sine x curve just goes in between minus 1 and 1, and y equals x, well, it keeps going. So we can clearly conclude that one. So putting together, x is always bigger than sine x, for x is greater than 0. That's just a touch on inequalities, ideas we've seen before using graphs. On Monday, we'll look at the fun stuff with inequalities, some things we haven't looked at yet. So there's an exercise 10C in the Cambridge, 10F in the Patel to play with.